Hello, this is Jack Jackson. In this video, we're going to be talking about a curvature of a curve in space, or possibly in a plane. So first of all, let's review a little bit about some things that we know about arc length. The arc length parameter, ds, is the square root of dx over dt squared plus dy over dt squared plus dz over dt squared. So you take those three derivatives with respect to t, square them, add them up, and then square root for ds. And then of course multiply that by dt. But you notice that part, including the square root and all the stuff inside of it, that is just the norm of the r prime of t, that vector derivative. Of course, that's also r prime of t is also known as the velocity vector. So ds is just the norm of the velocity vector dt, or in other words, the norm of the derivative of r dt. So the arc length s for some curve given from some t1 to t2, different values of our parameter, is just integrating ds over those intervals, which in terms of t is integrating from t1 to t2 of the norm of r prime of t dt, or in other words, the norm of v of t dt, integrating from t1 to t2. Now, by the fundamental theorem of calculus, we can measure the arc length s from t equals 0 to an arbitrary t, like we would measure the mile marker on an interstate highway. It's the distance along the highway, not necessarily an east-west or north-south distance, or definitely not a straight distance, because the highway is not a straight highway. So if we take an interstate highway, it starts, the mile markers say start at the western border of the state, and then they increase as we go to the east. The mile markers are measuring essentially what this S is measuring, the distance along the highway from the eastern border. Not the shortest distance to the western border, excuse me, but not the shortest distance, but the distance along the highway. So that's what this S thing is measuring, and of course that's just S of t is the integral from 0 to t of r prime of u, norm of that, du. Okay? Or, in other words, integrating the velocity curve. Okay? And this gives s as a function of t. And sometimes it's useful to solve this resulting formula for t in terms of s. Okay? And so that the curve can be written in terms of this arc length parameter s. And one nice thing about that is s is independent of whatever parameterization we use. So a smooth curve has no sharp corners. It has a continuous velocity, in other words, a continuous derivative. The unit tangent vector gives the direction of the motion along the curve. Since it has a unit length, length of 1 the whole time, really any changes in the tangent vector, the unit tangent vector t, this one right here that we're looking at, this t vector, any changes in that are really just changes in direction. So a smooth curve, which is part of a straight line, will have no change in direction. In other words, no change in the unit tangent. The unit tangent will be the same at every point along a straight path. But if the path has a sharp bend to it, it will have a pretty rapid change in the direction of the tangent, unit tangent. So curvature is going to sort of measure this. So we can think of curvature as measuring several different ways of thinking of it. The amount of curve, the amount that the curve deviates from straight, the rate at which the direction of the curve is changing, how tight the curve is, or you might say the rate of change in the direction of this unit tangent vector. So curvature, lowercase kappa, right here, is used for that, curvature. It's defined to be the rate of change in the unit tangent vector with respect to arc length. So that's dt vector over ds, and then take the norm of that. Well, let's look at a couple of ways we might want to think of it that way. But of course, using the chain rule, that dt over ds is dt over d little t divided by ds over d little t. So of course, dt over d big T over d little t is t prime of t, and ds over dt is just r prime of t, and we're dividing these two things, we can divide their two norms and to get the norm overall. So that last form there is a little bit more useful form than this first one up here. Okay. Now I want to see if I can get all of this ultimately in terms just of the r. So I'm going to do a little bit of derivation here on the next slide. So let's start here in the upper left corner. Remember that r prime of t is just the norm of r prime of t times that unit tangent vector. So r prime of t is well, the unit tangent vector is the derivative r prime divided by the norm of r prime, so it would make it unit. This is just solving that formula for r prime. And the norm of r prime is what is another way of saying that is ds over dt. It's how fast that length is changing, say with our time variable, if little t is time. Okay, take a second derivative. Then we're taking the second derivative of this last expression. Well, that's a scalar function times a vector function. We have a product rule that says it's the derivative first times the second plus the second times the derivative first. So the derivative first part is I'm not sure if I said that right. First times the derivative of the second, which is what I've got the second term, plus the second times the derivative of the first. Okay, the derivative of this first part is the second derivative of s with respect to t, and then that's times t. And then the other way around is you got the first term, ds, first factor, ds over dt times the derivative of that, which is t prime. And so it can be written that way. So what if we cross product these two guys and then take a norm of that? So for now, the norm is along for the ride. We're going to do the cross product and the inside. Working on the inside, r prime we see is, well, by this expression, it's ds over dt times t vector. And we want to cross product that with our double prime, which is given by this sum here. Well, cross product's going to distribute over a sum here. So it's this one times cross product this one plus this one cross product with that. So you have a distributive property there that works for cross products and sums. And this first part, since these are constants, constant functions, they can be brought out front of the cross product. So we can multiply those two constant functions and then cross product the two vectors that are left. And same way over here, we can pull those out. And over here, they're the same thing, so that just becomes ds over dt squared. Okay, so what do we have at this point? We've got the norm of ds over dt times the second derivative of s with respect to t times t cross t vector plus ds over dt, that scalar function squared, times t cross t prime. Now t cross t is 0. Any vector crossed with itself is going to be 0 there. Okay, and so that means this first term is wiped out. Okay, so now we just have the second term. Now t and t prime are perpendicular to each other. That's one of the things that we noticed earlier. And so if you have things that are perpendicular to each other, when you do the cross product, you're just multiplying their two norms. Okay. When you find the norm of this, when you do the norm of that, you're finding these two norms. So this norm here is going to be the absolute value of the first part, but since it's squared, we can drop the absolute value. Then the norm of this cross product. Well, the norm of the cross product is the product of the two norms times the absolute value of the sign in between, but they're perpendicular, so that part is just 1. So we have this here, ds over dt squared is the norm of t times the norm of t prime squared. But wait a minute, t is a unit vector, so the norm of t is 1, so that part can go away. And we see ultimately then that if we take r prime and cross product it with r double prime and then take a norm, it is ds over dt squared times the norm of t prime. Okay, so solving for the norm of t prime, that's this cross product of the r and the r prime, that norm divided by this ds over dt squared. Now, moving a little further, ds over dt is the norm of r prime. So we have the r prime of t cross with r double prime of t, took that norm, divided by the norm of r prime of t squared, that's the norm of t prime. Okay, now what does that have to do with curvature? Well, curvature is the norm of t prime divided by the norm of r prime. Okay, and so norm of t prime is this expression right here, and divide that by norm of r prime. Well, we already have a norm of r prime squared here, so that becomes norm of r prime cubed in the bottom, and the top is this. So ultimately, this gives us another formula, in fact, a more useful formula a lot of times back in terms of r, and this is for the curvature. So the curvature kappa is the norm of r prime cross r double prime, and then divide that by the norm of r prime cubed. Now, if we have a plane curve of the form y equals f of x, we're going to basically parameterize this where the t and the x are the same thing. So we have r of t, r of x, is just x comma f of x comma 0. So it's a vector in the xy plane, listed as a 3D vector, but because I'm going to do some cross products in a little bit. So it just has that 0 z component. So then r prime is pretty easy. The derivative of x is 1, the derivative of f is just f prime, and derivative of 0 is 0. So it's 1 f prime 0 for r prime. R double prime is then 0 f double prime 0. The derivative of 1 is 0, of course. The first derivative of f prime is f double prime. Okay, so if we do those cross products, if you cross product these two here, okay, you could think of this as a sum, i's and j's. This is I plus f prime j, and this is times f double prime j. If you distribute that, you get 1 times f, you get I times f double prime j. Okay, and here you have f prime times f double prime, and then you got a j times j. Well, j cross j is 0, so that goes away. There's nothing to worry about over here on the z's. And here you have an I cross j, which just is a k, and the size of it is just f double prime. So the cross product anyway, you can work that out. It's 0, 0, f double prime. Okay, so the norm of that is just the absolute value of f double prime, because it only has the one component there, so that's easy enough. So the norm of r prime, remember, is the square root of 1 plus f prime of x squared. Okay, that goes back to our arc length parameter, if you remember how that works. Okay, and so k, from our formula from the previous slide, is the norm of r prime crossed with r double prime divided by the norm of r prime cubed. Well, the top we see is just the absolute value of f double prime, and the bottom is, well, when let's see, we want to take, it's this thing, which is 1 plus f prime squared to the 1/2 power, and then we have to cube that. So it's 1 plus f prime squared quantity is raised to the 3/2 power. So there's a formula that can be used if specifically it's a plane curve where you've solved for y in terms of x. Okay, so this works in it's a very specific case. Okay, so summarizing, here are some of our curvature formulas. Okay, we define the curvature as the norm of dt over ds, the derivative of t with respect to the arc length parameter s. Excuse me, and take that norm. We could also do it as the norm of t prime divided by the norm of r prime, and that gives us a way we can always do it directly if we know those things. If we seeing it only in terms of the r's, then that was take r prime crossed with r double prime, take the norm, and then divide by the norm of r prime cubed. And for a specific case of a curve that's a plane curve of the form y equals f of x, then this reduces to, or is alternately seen as, the norm of f double prime, or that's just the absolute value, of f double prime divided by 1 plus f prime of x squared. The whole denominator is then, the whole expression is raised to the 3/2 for the denominator. We'll do some examples of some of these things in a later video, but I want to talk about one more thing about curvature first. Let's take the example of a curve that's in the xy plane, has a radius a, and it's centered at the origin. So r is given to be a cosine of t, comma a sine of t, comma 0. That's a standard parameterization that we've looked at before for parameterizing a circle of radius a centered at the origin. X is r cosine theta, y is r sine theta. Here I've already used r for something else, so I'm going to use a for the radius, and instead of theta we're going to call it t, our parameter. R prime then is just, see, the derivative of cosine is minus sine of the same argument, so it's minus a sine of t. The derivative of sine of t is cosine t, so that's a cosine of t for the second component and 0 for the third component. Notice that the norm of r and the norm of r prime are both a. We can factor out the a square, and we get cosine squared plus sine squared is 1, and then square root of the a squared is back to a. And of course that makes sense. If it's a circle, of course the radius going out is going to point to a distance. It's always going to have a length of a, but it also turns out its derivative has a length of a as well. So we know that the t vector is r prime divided by the norm of r prime. That's just our unit tangent vector. So the r prime is tangent, but then we divide by the norm. So we're just taking this vector for r prime right here and dividing by the a, so we distribute the a's are going to cancel out. So the t vector is minus sine of t, comma cosine of t, comma 0. So then we take a derivative of that. Let's see, derivative of sine is cosine, so this is minus cosine of t. Derivative of cosine is minus sine, so we have minus sine t and 0. So negative cosine t, comma negative sine t, comma 0 is t prime, big T prime. The norm of that, again, is 1. Okay, and if the norm of t prime is 1. We always know the norm of t is 1, but the norm of t prime is also 1. So the curvature is the norm of t prime, which is just 1, divided by the norm of r prime, which is a. So the curvature is 1 over a. So it doesn't really matter if we take the circle and take any circle of radius a, it's going to have the same, essentially basically the same result. So it turns out for a circle, the curvature is the reciprocal of the radius. So what that means is small circles will have a large curvature and large circles will have a small curvature. So as the radius of a circle approaches infinity, the curvature approaches 0. And that makes sense because as that circle gets bigger and bigger and bigger, the outside looks more and more and more like a straight line, which would have 0 curvature. And as that circle gets smaller and smaller and smaller, it gets tighter and tighter. It's a quicker and quicker change in direction as you go around it. So it gets a larger and larger curvature. So if we take any point on any curve and then take a circle that lies in the plane containing the unit tangent and unit normal vectors, the t and n vectors, at that point, and let's give that circle a radius 1 over the curvature of the curve that we're starting with. And let's also let one of the points be the point on the curve that we're talking about, and the center will be in that plane, right, that contains the normal and the unit normal and unit tangent vectors, and let the normal vector point toward the center of the circle. So put it in that direction. And that will be called the osculating circle. And the plane that it's in is called the osculating plane. And notice that the radius of this circle is the reciprocal of the curvature of the curve, 1 over k, and that is called the radius of curvature of the curve at that point. So let's visualize this in this next slide, where we see several of the copies or several versions of the osculating circles for different points along this curve. In fact, I'm going to look at this dynamically. And here we can see this curve. This particular curve is given by x equals t squared, y equals t cubed minus 3t. We kind of looked at that before. T is going from -2 to 2. And I can, by moving this slider, I can move the point around. Okay, and you see that for the moment I have turned on the unit tangent vector, which is the purple one, and the unit normal is the gray one. They're miscolored over here. I can actually fix that, I think. Get them colored correctly. Okay, now I've fixed that so the colors over here on the labels match the colors here correctly. So the unit tangent is the purple one, and the unit normal is the brown one. And here you see the osculating circle. So the radius of that circle is the radius of curvature, and its reciprocal is the curvature, which I have calculated and have displayed up here. So at this point, the curvature is about 1.61, which means the radius of this circle is 1 over that, 1 over 1.61. Okay, and the center of the circle is going to be in the direction pointed by this normal. So this normal vector, if you continue out that way, somewhere in here it's going to cross the center of the circle, about roughly in this area here. Okay, and so that's the osculating circle. At this point, the curve is changing pretty quickly, so it has a small curvature. If you look at it, if you look at the curve right here and look at this circle, they match each other pretty well. So this is the best matching circle to that curve at this particular point. Okay, and I can look at some different things. Now at this point, the circle is so close to being, the curve is so close to being a straight line that the circle is so big it's not actually even showing up. But I'm going to go ahead and animate this so that the t value is time, and it's actually tracing this out in real time. And you see it's going to start with a really huge circle, and the circles are getting smaller now because the t values are changing more quickly, and the radius of curvature is tighter there, and smaller radius of curvature, bigger curvature. Now we get some bigger radius of curvature, smaller curvature. We're down to 0.2 something, and now the curvature is getting bigger again. It's changing faster. The circle's getting smaller, and then It's going to start increasing again because the curve is getting flatter. It is getting less curvature and greater radius of curvature. Okay, one more time, let's go through that and just follow along with that and see what's happening. But as you see, as the curve curves more, it has a smaller radius of curvature, a smaller circle there, and but a bigger change in quicker change in that direction of that unit tangent vector. And then as it gets bigger here, that's when the curve's getting flatter and so forth. So here we're seeing we're changing faster and faster, tighter curve. We're coming out of that tighter curve now a little bit, so the circle's getting bigger and bigger, curvature is getting smaller and smaller, and this goes along here. So you can watch that if you want video, rewind that a couple times if you want, and you can pay attention to different things, like you can pay attention to the directions of the normal and tangent vectors. You can pay attention to the curvature here. You can pay attention to the size of those circles. Okay, so I think that gives you some idea now about what we mean by curvature. We have a few formulas for calculating it, and maybe in the next video we'll actually calculate it for a couple of different examples maybe.